Due to recent conflicts in the Middle East and the ongoing war in Ukraine, there has been a push to change how militaries defend their airspace. For decades, modern integrated air defense systems have relied primarily on kinetic interceptors, such as surface-to-air missiles to destroy airborne threats. This method can provide a high kill probability, provided the interceptor successfully navigates the kinematic intercept geometry. However, the proliferation of mass-produced, low-cost autonomous drones has broken the economic sustainability of kinetic defense. When an adversary deploys a swarm of 50 drones, each costing a fraction of the price of a single interceptor missile, a defense network will exhaust its magazine capacity long before it neutralizes the threat. For many counter-drone scenarios, the primary constraint is increasingly shifting from detection and kinematics toward magazine depth and cost per intercept.
To solve this problem, engineers have turned to the electromagnetic spectrum. By utilizing high-power microwaves and high-energy lasers, defense systems are constrained only by the availability of electrical power. They provide a virtually infinite magazine and a cost per shot measured in a few thousands of dollars. In this video, we're going to examine how these systems destroy targets using electromagnetism, some quantum mechanics, optics, and atmospheric fluid dynamics. To defeat a synchronized swarm of drones simultaneously, engineers must target the aircraft's reliance on microelectronics. This is achieved by the usage of high-power microwaves. High-power microwave weapons operate on the principles of electromagnetic induction, governed by Maxwell's equations and Faraday's law. Faraday's law states that a changing magnetic field induces an electromotive force, or voltage, in any nearby conductive material.
Maxwell-Faraday's equation relates a changing magnetic field to the circulation or curl of the induced electric field. High-powered microwave weapons project an intense, rapidly oscillating electromagnetic field over a wide physical area. When this field interacts with the internal wiring and circuit board traces of a drone, those metallic components act as receiving antennas. The oscillating microwave field induces high-frequency alternating currents and extreme voltage spikes directly within the drone's electrical system. Modern drones rely entirely on commercial off-the-shelf microprocessors constructed from complementary metal oxide semiconductors, or CMOS. The architecture of a CMOS transistor relies on microscopic layers of silicon dioxide, acting as gate insulators. These components are engineered to operate at very low voltages, typically between 1 and 5 volts. When a high-powered microwave pulse strikes the drone, it can induce hundreds or thousands of volts across the internal circuit boards. The induced voltage rapidly exceeds the dielectric breakdown threshold of the silicon dioxide insulators. The insulator fails, allowing current to punch completely through the gate structure. This failure mechanism causes an avalanche breakdown within the semiconductor p-n junction. The resulting uncontrolled current flow generates intense localized heating, which causes irreversible damage to the microprocessor. Without its flight control computer, navigation module, or electronic speed controllers, the drone loses navigation and flight stability. The microwave energy accesses these vulnerable internal electronics through two distinct coupling mechanisms. The first is front door coupling. Front door coupling occurs when the microwave radiation enters the drone through its intended radio frequency antennas, such as the GPS receiver or the command and control data link. Because these antennas are designed to capture electromagnetic waves and route them directly into the sensitive receiver circuitry, front door coupling requires relatively low power to achieve component destruction. However, front door coupling is most effective when the microwave energy overlaps the operating bands of the target's receiver systems. The second mechanism is backdoor coupling. Backdoor coupling does not rely on the drone's antennas. It relies on the imperfect shielding of the drone's chassis. Microwave radiation possesses wavelengths measured from millimeters to meters. This allows the electromagnetic field to penetrate the drone through any physical aperture, including ventilation seams, panel gaps, and unshielded sensor housings. Once inside the chassis, the microwaves couple directly to the unshielded wires connecting the battery, the motors, and the flight controller. The length of these internal wires often corresponds to fractions of the microwave wavelength, turning the internal wiring harness into an efficient, unintended dipole antenna. Backdoor coupling requires significantly higher radiated power than front-door coupling, and it's generally less dependent on the target's intended radio frequencies, but can remain effective even against systems employing conventional radio frequency countermeasures. Generating the massive power required for backdoor coupling over long distances involves specialized high-voltage engineering. A high-power microwave weapon does not require continuous output. It relies on extremely short pulses, often lasting only tens of nanoseconds, to deliver gigawatts of peak power. The generation process begins with a primary power supply, typically a diesel generator, which provides continuous low-voltage direct current. This current charges a bank of capacitors arranged in a Marx generator configuration. The Marx generator charges the capacitors in parallel at a low voltage over a relatively long duration. Once fully charged, a series of spark gap switches trigger simultaneously, discharging a lot of capacitors in series in a fraction of a microsecond. This transforms the low voltage input into a massive high voltage, high current electrical pulse. This high-voltage pulse is routed into a microwave-generating device, such as a virtual cathode oscillator, known as a vercator. In a vercator, the high-voltage pulse accelerates a dense beam of electrons toward a wire mesh anode. A large portion of the electrons passes through the mesh. Because the space behind the mesh is at a lower potential, the electrons rapidly decelerate, repel each other, and turn back toward the anode, creating a dense cloud of oscillating electrons called a virtual cathode. The continuous violent oscillation of this electron cloud generates intense microwave radiation. The microwave energy is channeled through a waveguide and emitted into the atmosphere by a directional antenna. Unlike a laser, which focuses its energy into a microscopic point, the microwave antenna projects a broad cone of electromagnetic energy. As the microwave pulse travels away from the transmitter, it is subject to the inverse square law. The power density of the field decreases proportionally to the square of the distance from the source. While this rapid attenuation requires the weapon to generate gigawatts of peak power at the source to remain lethal at range, the expanding geometry of the beam provides a massive tactical advantage. Because the beam naturally spreads out, the weapon does not require precise optical tracking or sustained dwell time. A single microwave pulse can encompass a large volume of airspace. If a swarm of 50 drones flies into this volume, the electromagnetic field interacts with all 50 airframes simultaneously. Sensitive electronics across multiple drones may experience transient failures in a span of a few seconds. Operationally, these systems attempt to create a temporary electromagnetic exclusion zone around defended airspace. Several modern defense systems are specifically designed around this one-to-many engagement philosophy. One example is the Leonidas system, developed by Epirus, which uses high-power microwave pulses to engage groups of drones simultaneously rather than intercepting each aircraft individually. Systems like these are intended to counter the growing battlefield use of coordinated, autonomous drone swarms. While high-power microwaves provide the volumetric area of effect required to defeat synchronized swarms, their rapid attenuation over distance makes them less effective against singular, heavily shielded targets at extreme ranges. For precision engagement over several kilometers, engineers are also testing sustained thermal energy transfer, which is the domain of high-energy lasers. High-energy lasers destroy targets by projecting a highly concentrated beam of photons. The core mechanism relies on quantum mechanical stimulated emission. In a modern military context, the preferred architecture is the solid-state fiber laser. A fiber laser generates its beam entirely within a flexible optical fiber doped with rare earth elements, typically ytterbium. Electrical power drives laser diodes, which emit a specific wavelength of pump light into the fiber. The ytterbium atoms absorb this pump light, elevating their electrons to a higher, unstable energy state. This creates a population inversion, where more atoms exist in the excited state than in the ground state. As these electrons naturally decay back to their ground state, they release photons. When one of these released photons interacts with another excited ytterbium atom, it stimulates that atom to release a second photon. These two photons are perfectly identical in wavelength, phase, and direction. This process multiplies rapidly within the optical cavity, resulting in a spatially and temporally coherent beam of monochromatic light. Producing a high-power beam requires the aggregation of multiple laser sources. A single optical fiber can typically output only a few kilowatts of power before the thermal load degrades the glass structure. To achieve the 50 to 300 kilowatts required for military interception, engineers utilize spectral beam combining. Multiple individual fiber lasers, each operating at a slightly different wavelength, are directed into a diffraction grating. The grating merges these disparate beams into a single, combined output beam while preserving sufficient beam quality for long-range targeting. The lethality of this combined laser beam is dictated by its irradiance, measured in watts per square centimeter. Irradiance is the total power of the laser divided by the cross-sectional area of the beam at the exact point it strikes the target. To maximize irradiance, the beam must be focused into the smallest possible spot size. The minimum achievable spot size is governed by the Rayleigh criterion for the diffraction limit. The minimum beam divergence is fundamentally limited by diffraction. For a circular aperture, the diffraction-limited divergence angle scales approximately with the laser wavelength divided by the aperture diameter. This is why long-range laser systems require large beam directing optics. When the focus beam strikes the surface of a drone, the material composition of the target dictates the outcome. The surface absorbs the photons, immediately converting the electromagnetic energy into thermal energy. If the irradiance is high enough, the temperature of the material rapidly exceeds its melting point. For a drone constructed from aluminum, the laser must sustain its position on a single physical coordinate until the structural integrity of the metal fails under aerodynamic load. For a drone constructed from fiberglass, carbon fiber, or epoxy resins, the intense heat causes rapid pyrolysis and combustion. If the beam is directed onto the lithium-ion battery packs or the aviation fuel tanks, the thermal transfer triggers a cook-off, causing catastrophic failures. This process requires a continuous dwell time. The laser must hold its focal point perfectly steady on a moving target for several seconds to transfer enough thermal energy to achieve structural failure. Propagating a highly coherent beam of light over several kilometers introduces severe physical limitations. The atmosphere is a turbulent fluid composed of gases, water vapor, and particulate matter. When the laser leaves the aperture and enters the atmosphere, it experiences immediate degradation through absorption and scattering. Water molecules and carbon dioxide actively absorb photons in the near-infrared spectrum, converting the laser's energy into ambient heat. Furthermore, the beam experiences Rayleigh scattering as it interacts with gas molecules, and Mie scattering as it interacts with larger aerosols like dust, smoke, and atmospheric salt. The absorption of the laser energy by the atmosphere creates one of the most significant engineering challenges in directed energy weapons: thermal blooming. As the high-energy beam travels through the air, it heats the air column directly in its path. The heated air expands, causing a localized decrease in air density. A decrease in density results in a decrease in the refractive index of the gas. The cooler, denser air surrounding the beam maintains a higher refractive index. This gradient causes the air column to act as a diverging lens. The atmosphere actively bends the laser beam outward, spreading the photons over a larger area and destroying the tight focal spot required for high irradiance. The higher the power of the laser, the faster it heats the air, and the more severe the thermal blooming becomes. Simultaneously, the beam must contend with atmospheric turbulence. The sun heats the surface of the Earth unevenly, creating rising columns of warm air and descending columns of cold air. These turbulent eddies possess varying refractive indices. When the laser passes through these shifting pockets of air, different portions of the wavefront travel at slightly different speeds. The beam undergoes severe phase distortion. The focus spot on the target degrades into a fragmented, fluctuating pattern, drastically reducing the total energy delivered to the structure. To counteract thermal blooming and atmospheric turbulence, defense systems implement adaptive optics. The laser weapon is equipped with a Shack-Hartman wavefront sensor, which utilizes a secondary low-power illumination laser. This secondary laser strikes the drone, and the reflected light travels back through the exact atmospheric path the primary weapon laser will take. As the returning light passes through the turbulence and thermal gradients, its wavefront is distorted. The Shack-Hartman sensor measures the exact phase aberrations of the incoming wave. A high-speed processor analyzes these aberrations and transmits the corrective data to a deformable mirror positioned in the optical path of the primary high-energy laser. The deformable mirror sits on a grid of hundreds of piezoelectric actuators. Based on the data from the wavefront sensor, these actuators push and pull the surface of the mirror, altering its shape by fractions of a micrometer. The mirror applies a conjugate phase distortion to the outgoing high-energy laser beam. The laser enters the atmosphere intentionally pre-distorted. As it travels through the turbulent air and the thermal blooming gradients, the atmospheric aberrations precisely cancel out the pre-distortion. By the time the beam reaches the target, the wavefront has corrected itself into a flat, highly focused point of light. This closed-loop process occurs hundreds of times per second, allowing the laser to partially compensate for atmospheric distortion and maintain beam quality under many operating conditions.